So the next problem that we had in the test was it says that a cylindrical hole is bored through the center of a sphere, and we want to find the volume of the remaining portion of the sphere. Now there are a number of ways you can do this. The method that I'm going to use is the method of cylindrical shells. It's very possible to use the cross-section method that we used on the last problem, but I'll just go with this one. So if I draw at least the XY planes cross-section of a circle, cross-section of the sphere, I should say, I've got this shape with, let's say, radius big R, but there is a cylindrical hole cut through the middle of the sphere. So I need to erase out the top portion and try to make that even. And then we'll have a cylinder inside the sphere at some radius small r. So my best attempt at drawing the images here. So if I want to do cylindrical shells, what I want to do is just look at the top half of the sphere and put a cylinder that's really thin right here. And that'll get the volume of a very narrow portion of the shape. Okay, doing my best at drawing it. It's not so easy to do here. But if we look at this little shell that we've got and we unroll it, the height will be the height of this little red portion I've drawn. And notice that as I make more of these shells, this little point at the bottom will go from left to right. So in the end, I'm going to integrate with respect to x from small r to big R. And I'll be multiplying by 2 because what I've started up here is just the top half. Now, again, the height of the little shell is this thing. And I know the formula of a circle is y equals the square root of the radius squared minus x squared. So that's my height. And my radius of my little shell here is x. So this portion along the bottom of the shell is the circumference of that circle. So 2 pi x. And again, if I've unrolled this little cylinder, the depth of it is going to be dx. So putting all this together, I have 2 pi x times the square root of r squared minus x squared in my integral. And once I have this set up, there's not a whole lot more thinking we have to do. It's just a bit mechanical. So if I factor out constants, I'm left with this. So to make this integral easier to do, what I would recommend is u substitution, where u is everything that is inside the root. Therefore, du will be negative 2x dx. And I'll write negative 1/2 du equals x dx. because x dx is in my integral, so when I switch to du, I'm going to introduce that extra factor there. Sorry, so we've got 4 pi, and then I'm going to put that extra factor that we came up with. And I'll have the integral of u du, and the only thing we have to worry about is the limits of integration. But we just plug them into this u equals r squared minus x squared, where each one goes in where r was. So that makes the top r squared minus r squared, big r's, so they go away. The bottom becomes r squared minus little r squared, and that's where we are. So we've got negative 2 pi. The integral will be u to the 3/2 power times the 2/3 factor at the front. And we're here. So negative 4/3 pi times 0 to the 3/2 minus r squared minus little r squared to the 3/2. Altogether, this is going to be 4/3 pi times this r squared minus little r squared to the 3/2 expression. And that is the volume of the shape that we've got here.